let's see that let us record one sample voice. Okay, let's say our voice is, hello, good morning, this is a sample message from Rupam Integrated Ideas. So what we are going to do is we are going to take this file, let's say sample1. Okay, let us save it in a Matlab directory. Okay, so first thing we need to do is we need to change the directory to our project directory. Our project directory at this moment is audio process. So let's change our Matlab directory to audio process directory. Let us take a new script. Let's call this phase1.m. Let's call it phase1.m. So in Matlab, I want the user to select and give a file as input. Okay, so we can write fname path equal to UI get file star dot star, that means all the type of files, and we can ask the user please enter message okay. So what is UI get file is, it is going to open a file open dialog where it will save the directory and file name. If I concatenate the file name with the directory, I will get the total file. Okay, so actually my file name is equal to string concatenation of path with file name. I can read any web file in Matlab. Say w is equal to web read fname. Okay, and I can so in Matlab 2016 onwards, web read function has been eliminated. Instead, we have a function called audio read. So whatever file name user has selected, we are going to give that as input to audio read function. It returns two values, the amplitude and the sampling rate. Now standard audio signals may be of stereo channel or mono channel. Okay, that means one channel recording, two channel recording. They may be of 8 kilohertz, 16 kilohertz sampling frequency. So you need to read both of them. Say sampling frequency fs. So the audio read function will read and give this file. Now there is one more function by name So we have one more function, audio player, okay, for playing such files. Okay, so let's see how the audio player works. In Matlab, you can press F1. You can create an audio player by passing it with y. Y is nothing but w over here, the wave values, and sampling frequency, which is fs. And then if you say audio player dot play, that is player dot play, it's going to play the files. If you come down, if in the play command you pass the player, it's going to play that file. So player, that's it. Let's save this. I'll run this. Okay. So what we are able to do, we are able to take one audio file from the user and we have played that using Matlab. So we've learned that before any programming, it is always good to just use two comment statement and write what you are doing in this code block. Ask for an audio file and play the file. But before that, let us take CLC, clear all and close all. Now what is significant about this audio file is this Y that you are seeing, this W that you are seeing, this is the amplitude, this is the waveform. So let us plot this waveform. Plot W. So let's again run this, take this waveform. Good morning. This is a sample message from Rupam in integrated ideas. Okay, you'll see many spaces in between. Why it is green color? Because it is a stereo channel. You've got two channels of data over here, and if you look at them, this is the sample, this is the modulations. Okay, so this is how the voice is being played out. This is how the audio signal looks like. But the same thing, if I speak next time, I cannot give same amount of pause, right? It might appear early, and with the same intensity I cannot speak hello, right? I might be little slow, little fast. So whatever way it is, the signal will vary in the time domain. Okay, therefore we generally use a frequency domain characteristics. Okay, now how to work with this? Now you are seeing, as we are playing with this audio file, I mean as we are playing, the audio is trying to play this signal. What is our intention is? Our intention is to encrypt this audio. Okay, and we are going to use a very low end encryption, that is substitution based encryption. Okay, see, if you look carefully, this audio file, that is W, is a 2-channel data, with different values, 2.8 into e to the power 09, 2.8 into 2 to the power 08, so and so. But this is a 2-channel data. Why? Because this is a stereo signal. Okay, the first thing for any of the audio signal processing, one of the better thing is to do is normalize the signal. The meaning of normalization is so see, if you plot W, if you just plot W, you'll see that the values are 0.06, minus 0.06, 0.08, so and so, so and so. And when you see these values, by double clicking, minus 2.8 into 10 to the power minus 8, minus 7.68 into 10 to the power minus 8. So the values are quite small in range. Some values are 0, some values are, I mean, there is nothing called 0, some values are 0.68, okay. So it is always a good thing to normalize the signal. The normalization means taking the signal, okay, and bringing its value between 0 and 1. How can you do that? Suppose you have a number 3, 4, 5. The largest number is 5. If you divide all the number by the largest number, 3 divided by 5, 4 divided by 5, 5 divided by 5, automatically all the numbers will be between 0 to 1 range. So generally what we do is, one of the common thing we perform for any audio signal processing is called the normalization. This is one of the part of pre-processing step, okay. Normalization. This is pre-processing step 1, normalization. So how do you normalize? We have two channels, okay. So for, let's take number of channel and length is equal to size of W. Sometimes your recording must be mono also. For instance, the mic that I am using, it might record in a mono channel. In that case, W will be only 4, 1, so and so into 1. Okay, only one audio channel might be there. So for all the channels, for I is equal to 1 to number of channels that you have, first I am taking a particular channel's data. Say W1 is equal to W of I comma colon. That means first time all the data of the first channel. Okay. Let's calculate the max. Mx is equal to max of absolute of W1. Why absolute? Because W1 will also have negative values. Okay. Now W1 is equal to W1 divided by Mx. So we are dividing the value with the maximum value, and then W of I comma colon is equal to W1. Okay, so W will be replacing with this. Having done so, let's display a message. Let's call signal normalized, and let's plot it differently. Figure plot W. So you can see the difference between the normalized and non-normalized signal. Let's take this as example. Now so W is, no, something is wrong. Made some mistakes here. 1 second. Mistake sample. Oh, actually W is a column. I mean, in one column one channel is there, in second column next channel is there, but instead of doing that, here we are taken row wise data. Okay, number of channel is actually in the columns. Okay, so for W1 is equal to I All right. Now let's run this again. See the difference, there is no change in the signal, isn't it? The graph looks same, right? Don't they? So see, there is no difference between the waveforms. But if you look clearly, here the values are between 0.06, 0.08, but here the maximum value is 1, the minimum value is -1. All the values are between 1 and -1. And even after normalization, there won't be any effect in the signal. So if I play the signal, that is hello, good morning, this is a for integrated ideas. Hello, good morning, this is a sample message from Rupam Integrated Ideas. So even after the W is changed, what we understand is that there won't be much difference between how the signal is sound, but all the values will be between 0 and 1. Now audio signal shows a linear property. What?
Sir, by normalization, what we do, sir? We are
By
compressing the audio.
no, not compressing. We are fixing the audio range. Okay. See, earlier the audio might be, some audio might be having low amplitude, some audio might be having high amplitude. Okay. By normalizing it, you make sure that their range remains same. Okay. All the values are between, say for instance, a particular range to a particular range. Now, if their range are fixed, all the values will be between 0 and 1 only, no? So you have a fixed range of values. Okay. Now, you see, if I multiply W, say capital W is equal to W into some big number, something like, let's say, 16,000, okay, and or let's say 32,000, and if I convert them into unsigned integer 16-bit, how the W will be? The W will be having fixed range, capital W. All the values which are too small will become 0 and all the values. Now, if you plot capital W, let's say W is equal to W into 1000 instead of unsigned, because unsigned will strip it, let's say floor. So if I floor them, you see, now there is no decimal number. Okay, all are integer values. There is no decimal number, right? But if you wave play, if you play the signal, that is hello, good morning, this is a sample message from Rupam Integrated Ideas. So this is capital W, and if I this is a sample message from Volume Okay, let me play. Okay, so the audio is no more clear, right? This is a form of encryption. So how did we perform the encryption step? How did I perform the simple encryption? We are taking encryption, linear encryption. Let's say our key is equal to 32,000. Okay, we did it by taking encrypted signal is equal to W into key. Okay, let's take a little bigger key. Okay, okay, or key. Okay, this is our encrypted signal. So there is not much difference over here, but if you play the encrypted signal, that is, let's say, let's play this signal.
This is a sample message from Integrated Ideas.
So encryption is just by means of which you degrade the quality of the audio such that it is not audible anymore, or it is not no more clear. What if I perform a reverse process? En, say, divided by key. So the key we had declared was 32,000. Let's divide it by the key and let's say DEC. Hello, good morning. This is a sample integrated ideas. Okay, this is the simple decryption process. This is a linear decryption because the decryption is just the inverse process of the encryption. Here this is a linear decryption because what I have done is I have simply divided the En value with my key and playing this sample, and again you'll be able to recover back the original signal. But the essence is plot en comma hold on plot bec colon comma 1, only one channel I am showing with green color. Let's put a legend. Let's put legend encrypted and decrypted. Let's run this. Let's run this once more.
This is a sample message from Root of Integrated Ideas. So decrypted message is same as the encrypted message, but I mean, look, the encrypted message was extremely big, okay, and the decrypted message is smaller in comparison. So what happens is, if you increase the amplitude of the audio signal tremendously high, the amplifier will not be able to handle that kind of audio. So even though the signal remains same, it is an encrypted message. You will not be able to hear this. Okay. So this is how a simple encryption and decryption and in audio is performed without changing on their properties. So in the